This is a lesson on what exactly a buffer solution is and also how to calculate the pH when we disturb a buffer solution. So a buffer solution, if I take a weak acid, for instance acetic acid, and because it is a weak acid we get an equilibrium reaction, H plus plus C2H3 O2 minus. And if we place into a container acetic acid, now most of that acetic acid is going to stay bound up. Only a real small amount of that would ionize. And this would be kind of representative, and if I took one of these and I broke it apart, that would be 25%. But typically with most of the molarities that we work with, we're not even going to see 25%. We're going to see things less than 5% ionized. Now, that's not a buffer solution. That's a weak acid. So if I put that back together, what makes a buffer solution is when I add a common ion, a conjugate to, in this case, the weak acid. So I'm looking for the conjugate base of that weak acid. So I'm looking for a source of acetate. Knowing the solubility rules, everything out of group 1A as an acetate, as well as most other acetates, are aqueous, so I'm just going to use sodium acetate just to keep it simple. So if I put these in, and these represent my sodium acetates, then those, they're going to go ahead and they're going to break into ions in solution because that's a sodium salt. Now again, the sodiums are really just a non-factor here, so I've got my acetic acid on this side, and I've got my sodium ions, the pink ones, and then I got my acetate ions down here at the bottom. Now, if I represent this page as a 1 liter container, right now I've got an initial concentration of 4 molar acetic acid, 4 moles per liter, and I've got a 3 molar sodium acetate. Now again, how we would make that solution, there's a lot of different wording, but when I get all this in there, I'm still at a total volume of 1 liter, and I've got 4 moles represented for acetic acid, 3 moles represented for my sodium acetate, specifically this conjugate base of my weak acid that we have here. And that's what makes a buffer solution. Now, why it's a buffer solution is because we can disturb that. We can take that buffer solution and we can do things to it. So I'm going to let this represent hydrochloric acid. So if I put that in there, then it, of course, immediately, it's going to ionize. And when I place that into solution, now I've got this extra H plus floating around, and by adding an additional H plus, that's going to shift the equilibrium back to the left. So what's going to happen in terms of the stoichiometry, which we'll get into the math of that here in just a moment, is I'm now going to go to 5 molar concentration initially before I ever get to doing the equilibrium problem. So this is stoichiometry first. Again, I'll show you that here in just a moment with the mathematics. So I'm going to get 5 molar acetic acid, and now I'm down to only 2 moles per liter on my acetate. So I added that and it shifts. Now again, it's not going to be a big change in the pH, and we're going to see that. We're going to go through some problems where we actually calculate the pH of those solutions, because buffer solutions can essentially consume up an additional H plus from, in this case, hydrochloric acid. On the other hand, maybe I throw a sodium hydroxide into this once it's established at 4 and 3, back to the original problem. I put in a sodium hydroxide. Again, that's a strong base, so that's going to be broken into ion form. And now, when we have that, we've got this hydroxide, and essentially it's removing an H. It's going to bind up one of those H pluses to make a water molecule. So understand this from Le Chatelier's principle. Adding a hydroxide is the same thing as taking away an H plus. By adding that additional OH, we shift equilibrium to the right. We remove some H+, binds that up, and now what we notice is we're down to 3 moles per liter of our initial weak acid that we started with, but now we're up to 4 moles per liter of acetate ion. So we can see here how adding an H+, definitely directly there in the expression, real easy in terms of Le Chatelier's principle. Adding hydroxide, taking away an H+, same thing, shifts this to the right, so we can see how that buffer solution behaves. We'll get into some of the calculations with that now. So the first calculation that I'm going to do here is just with the mixture before we've added any H+ by way of hydrochloric acid or any sodium hydroxide. This is just my buffer solution. This buffer solution is 4 molar in acetic acid, and it's 3 molar in terms of the acetate ion. Now, in order to find the pH, we're going to do an ice table. There's no H+ initially. We've got to find what that value is to get the pH, so we know it's going to increase by some amount, giving us an equilibrium value here of X. This 3 molar is also going to go up by X, 3 plus X, and then this one's going to go down by X, 1 to 1 to 1, so this is 4 minus X. The Ka value for acetic acid is 1.8 times 10 to the negative 5th, so that's equal to X times 3 plus X over 4 minus X. Now, when we start making these buffer solutions, the X compared to the molarity of the initial concentration of acetic acid and acetate ion is really a negligible amount. It's going to be a really, really small amount. So to avoid having to do the quadratic formula in this equation, there's a really simple thing we can do. We can say 3 compared to X, the X is insignificant. 4 compared to X, the X is insignificant. Now, makes it a little bit easier for us to solve for the value of X. So 1.8 times 10 to the negative 5th, and I'm going to multiply both sides here by 4. So times 4, and then I'm going to divide by 3, and I get that the X value is 2.4 times 10 to the negative 5th. So to calculate the pH, negative log of 2.4 times 10 to the negative 5th and I get the pH is equal to 4.6 if I do 1 sig fig, since that's what I had up there, 4.62 if we want to go ahead and tack on another one there just for comparative purposes. Now the next one of these I want to do, because it's really, really important that you understand this, because you will see this from time to time. I want to change this problem just a little bit and say, okay, what if we had the exact same concentration, in this case 3 and 3? What would this problem look like if I change those to where both of those values were 3? Now, just going down through the math here, the only thing that it changes is this becomes a 3, this is a 3, but now when we get down here, this value is a 3, and we got a 3 over 3, so those cancel. So when the initial concentration of your, in this case, weak acid and conjugate base, when those are the same, regardless of what they are, when those are the same, X is your Ka value. X is equal to Ka. When these two values are the same, X is Ka. Or we say pH is equal to the negative log of Ka, which is called pKa. So we can find the pH simply by taking the negative log of 1.8 times 10 to the negative 5th. Again, that's because we had 3 molar and 3 molar equal concentrations of weak acid and conjugate base. So in this case, negative log of 1.8 times 10 to the negative 5th is a pH equal to 4.74. Alright, so we're back to that original mixture again here, and now we're going to go in and we're going to add in the HCl, and we're going to look at what happens when we add the HCl. Now we already said adding in an HCl, an additional H plus drives this back to the reactant side. So what's going to happen is these two are going to form an additional HC2H3O2 before we ever start the problem. Now, one of the real common things is to immediately, because you've got, a scenario here where we've got a weak acid and a conjugate base, immediately we start thinking equilibrium. But when we're adding something in this case HCl, the first thing we have to think about is stoichiometry. The stoichiometry is always going to be first. So we've got to take a look at the two things we have here. We have HC2H3O2, and we have C2H3O2 minus, the conjugate base. So which of those is going to react with an acid? Is the weak acid or the conjugate base going to react with an acid? And it's the conjugate base. The conjugate base is going to react with that acid. So the first thing I'm going to do here before I ever set up an ice table or anything about equilibrium, I'm going to start by writing a reaction. HCl added to C2H3O2 minus, single arrow, stoichiometry first, HC2H3O2, and then the Cl minus, spectator ion there. So now we've got to go in and we've got to account for these. So again, this is a 1 liter container. So I've got all these in my 1 liter container, and I had 1 mole per that liter of HCl. I had 3 acetate ions, and I had 4 of those HC2H3O2. Stoichiometry first, then we'll do an equilibrium reaction and an ice table. So in this reaction, it's going to drive this way. This is going to happen. We've already talked about that from a standpoint of the Legos, what's going to happen. Now we're actually going to see it happen here mathematically. So we're going to react that HCl. It's limiting. It's completely gone. And then also we're going to react it with one of those acetates, leaving us with 2. On the other hand, on the product side, this one's going to go up by 1, and we now have 5 molar of the HC2H3O2. So now, after I've done all of that, now, and only now, am I ready to start talking about equilibrium. So now I'm going to write my equilibrium equation. And I'm going to plug in those values where I now have 5 molar here, none there initially, and 2 molar for that one. So this is my initial value, change and equilibrium. So the change, this is going to go up by x, x to plus x, down by x, so 5 minus x, and now I'm ready to set that up and solve. So Ka, 1.8 times 10 to the negative 5th equals x times 2 plus x, I'm just going to call it 2, we've already talked about what happens there with those values, over 5 minus x, again, simply just 5. It eliminates quadratic formula. Not that you can't do the quadratic formula, you're more than welcome to do so, but you'll find that given the magnitude of these Ka values and also factoring in Le Chatelier's principle, it's a lot of extra work to do the quadratic formula, and you really won't get much different in terms of the answer. So 1.8 times 10 to the negative 5th, multiply both sides by 5 to get rid of it, and then divide by 2. And I get 4.5 times 10 to the negative 5th. X equals 4.5 times 10 to the negative 5th, and therefore the pH, negative log of 4.5 times 10 to the negative 5th, is 4.35. And again, I know I'm going an extra sig fig there compared to what I started with. Now, a moment ago, we did this calculation for a 4 molar and a 3 molar without adding any HCl in, and we found that the pH of that was 4.62. But now when we add the HCl, kind of as expected, we're going to get something more acidic, but it's not way more acidic. It's not, if we had a 1 molar solution of HCl by itself, we would have a pH there of 0. But by adding in that 1 mole to this buffer solution, yeah, it lowers the pH from 4.62 to 4.35, but it's not a big gigantic change. Again, buffer solutions can resist small disturbances.